one of the deepest mysteries of science. Was there anything before the universe began? The Big Bang Theory proposes that our universe formed approximately 13.8 billion years ago, expanding from an unimaginably hot and dense state into the vast cosmos we observe today. This beginning was defined by the rapid cooling of the universe and the formation of the first fundamental particles. However, the moment before this cosmic birth remains shrouded in uncertainty. Time and space themselves may have come into existence with the Big Bang, meaning that our current laws of physics cannot see beyond that point. Yet human curiosity compels us to keep asking the question. Scientists and philosophers have long debated whether the Big Bang represents a true beginning, or merely one chapter in a much larger cosmic story. In this documentary journey, we will explore what modern science reveals about the origin of time, examine new discoveries about the early universe, and consider bold theories that extend beyond the Big Bang. First, according to our current scientific understanding, the 0 point of the Big Bang represents the beginning of our universe. In a single instant, all space, time, energy, and matter emerged from a point of infinite density. Within a tiny fraction of the first second, the universe entered a phase of rapid expansion, spreading faster than the speed of light across the expanding fabric of space. This early inflation shaped everything that followed. 1 second after the Big Bang, the universe was a hot, dense mixture of particles. Within minutes, the first light chemical elements formed in a process known as primordial nucleosynthesis. The early universe was extremely hot and dense, so hot that atoms could not remain bound together. Light, or photons, were constantly scattered by free electrons and could not travel far. For the first few 100,000 years, the universe was essentially foggy and opaque. As expansion continued, the cosmic environment cooled. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This moment, known as the era of recombination, changed everything. With electrons now bound into atoms, light was finally able to travel freely through space. The fog lifted, and radiation streamed across the universe. This ancient light still surrounds us today as a faint glow in the microwave range, stretched by billions of years of cosmic expansion. It is known as the cosmic microwave background, or CMB. Quite literally, it is an image of the universe in its infancy. By observing the CMB, scientists can see the universe as it appeared when it was only about 380,000 years old, and almost newborn compared to its current age of 13.8 billion years. It is the oldest light we can observe. The CMB is a fossil image of the Big Bang's primordial fireball. Discovered in the 1960s, it has since been studied in increasing detail by satellites and telescopes, providing a vast source of information. The seemingly random pattern of tiny temperature fluctuations across the sky is not random at all. These variations contain the seeds of the cosmic structures that would later form. Regions that were slightly denser eventually collapsed under gravity, giving rise to galaxies and galaxy clusters. In essence, the CMB offers a blueprint of future structure, revealing peaks and valleys in the original distribution of matter. It also informs us about the composition of the universe. Decades of research have shown that stars, planets, and ordinary matter like us make up only about 5% of the universe. The rest is dark and mysterious. Based on precise measurements of the CMB, scientists estimate that about 27% of the universe consists of dark matter, while roughly 68% is dark energy. Interestingly, new observations continue to refine this picture. In March 2025, scientists from the Atacama Cosmology Telescope, ACT collaboration, and Princeton University released the most detailed images of the CMB ever obtained. These images have 5 times the resolution of the full sky map produced by the Planck satellite, offering the clearest view yet of the universe's earliest moments. CEO's extensive survey data also captured the polarization of the CMB, information that reveals the directions of light waves and the motion of matter in different regions of the young universe. As ACT Director Dr. Suzanne Staggs explained, previously we could see where things were. Now we can see how they were moving. These high-resolution images illuminate subtle variations in the density and velocity of primordial gas, fine details of the original peaks and valleys. Such data play a crucial role in answering long-standing questions about how our universe transitioned from simplicity to complexity. It is truly remarkable that by measuring light that has traveled for nearly 13 billion years, we can observe the universe on cosmic scales as it existed only hours after its birth. But if the CMB represents the thermal radiation of the infant universe, what happened next? After recombination, the universe entered a truly dark period. Once the primordial glow faded, no new light sources existed as stars had not yet formed. This era ended when the first generation of stars ignited, likely around 100 to 200 million years after the Big Bang. These first stars, often referred to as population 3 stars, were probably massive, short-lived, and extraordinarily bright. They formed within protogalactic clouds, marking the beginning of galaxy formation. Astronomers call this era the cosmic dawn, the moment when starlight first pierced the cosmic darkness. Today, thanks to powerful new telescopes, we are finally beginning to observe the cosmic dawn directly. Launched in 2021, the James Webb Space Telescope was designed to detect the faint infrared light of extremely distant galaxies. Because light from the early universe is stretched or redshifted into infrared wavelengths, Webb's instruments are ideally suited for this task. Since becoming operational, JWST has shattered records by discovering galaxies that existed just a few hundred million years after the Big Bang. One such galaxy, discovered in 2025 and named MOMZ14, is currently considered the most distant galaxy ever observed. Its light dates back to just 280 million years after the Big Bang, meaning we see it as it was when the universe was only about 2% of its current age. That light traveled approximately 13.5 billion years to reach us. JWST's instruments finally captured it. More broadly, since beginning operations in 2022, JWST has found far more bright early galaxies than scientists expected. This unexpected abundance has energized the scientific community and raised fundamental questions about galaxy formation during the universe's first 500 million years. Each new high redshift galaxy adds another piece to the puzzle of how cosmic structure emerged so early. Observations suggest that MOMZ14 was undergoing rapid star formation at the time we see it. Its chemical composition, rich in nitrogen relative to carbon, resembles that of ancient globular star clusters in the Milky Way. This hints that stars may have formed differently in the earliest epochs. These findings are forcing astronomers to rethink how quickly the tiny fluctuations seen in the CMB could evolve into full-fledged galaxies. Were stars and galaxies forming more efficiently than we assumed? Or is our cosmic timeline incomplete? As new observatories come online, we hope to probe even deeper into the early universe. Yet no matter how powerful our telescopes become, we will never directly observe conditions before the Big Bang. For that, we must turn to theory. Over billions of years, matter has assembled under gravity into a vast cosmic web. Galaxies are not evenly distributed. They form filaments, walls, and enormous voids. This web-like structure can be traced back to the initial fluctuations seen in the CMB. According to standard cosmological models based on the Big Bang and a dark matter-dominated expanding universe, there should be a maximum size for coherent cosmic structures. The cosmological principle, a cornerstone of modern cosmology, states that on very large scales the universe should appear homogeneous and isotropic. Averaged over hundreds of millions of light years, the universe should look roughly the same everywhere. Standard theory predicts that the largest coherent structures should be no more than about 1 billion light years across. That is why astronomers are surprised when they find structures exceeding these limits. In 2024, researchers discovered a colossal ring-like structure of galaxies known as the Big Ring. It spans roughly 1.3 billion light-years in width, has a diameter of about 4 billion light-years. and lies at a distance corresponding to around 9.2 billion years in look-back time. Nearby lies another enormous structure known as the Giant Arc, stretching about 3.3 billion light-years. To put this into perspective, the diameter of the Milky Way's own supercluster is only about 0.5 billion light-years. The Big Ring and the Giant Arc are truly immense. Further analysis suggests that the Big Ring may not be a perfect ring at all, but perhaps a spiral or helical structure in space. If it were visible to the naked eye, though its distance and faintness make this impossible, it would appear about 15 times larger than the full moon. Such features are difficult to explain even with our best theories. The Big Ring is too large and complex to be accounted for by simple acoustic oscillations in the early universe. If confirmed, these structures may require us to rethink the assumption of large-scale homogeneity. As their discoverer, Alexia Lopez, noted, their immense size and unusual shapes are not easily explained by our current understanding of the universe. They must be telling us something. But what? One possibility is that these superstructures are rare statistical flukes, random overdensities larger than expected, but the discovery of multiple such structures makes this explanation increasingly unlikely. Other examples include the Sloan Great Wall, the South Pole Wall, and enormous quasar groups. Another intriguing possibility is that they point to new physics or unusual conditions in the early universe, beyond standard inflation theory. For instance, hypothetical ultra-thin defects in spacetime formed after the Big Bang, if they exist, could have influenced the large-scale distribution of matter. While speculative, such ideas represent attempts to explain these anomalies through new physics. An even more radical proposal comes from physicist Sir Roger Penrose. He suggests that these structures might be traces of a universe that existed before our own. In his conformal cyclic cosmology model, the Big Bang is not a beginning, but a transition between cosmic eras. According to Penrose, circular patterns in the CMB could be evidence of gravitational waves from events in a previous universe. Although most cosmologists remain skeptical, the very existence of these anomalies suggests that we do not yet fully understand early universe physics. Let us summarize what we have learned so far. The Big Bang represents the moment when the universe began expanding. For the first few billion years, this expansion slowed due to gravity. But in 1998, scientists made a startling discovery. The expansion was accelerating. Something unknown, now called dark energy, was pushing the universe apart, overpowering gravity on the largest scales. Today, dark energy remains one of the greatest mysteries in cosmology. For a long time, the simplest assumption was that dark energy is a cosmological constant, an inherent property of space itself, possibly linked to vacuum energy. The widely accepted lambda CDM model assumes that dark energy remains constant over time, causing the universe to accelerate forever. However, recent data suggest that this may not be the full story. Observations from the Dark Energy Spectroscopic Instrument, DCI, which studies millions of galaxies and quasars, indicate that the influence of dark energy may be changing over cosmic time. In early 2025, scientists analyzing 3 years of DC data reported evidence that dark energy may be weakening over billions of years. If true, this would mean that cosmic acceleration might not continue indefinitely. It raises profound questions about the future of the universe. Will expansion eventually slow down or stop? Could gravity regain control, leading to a future collapse? We do not yet know. What is clear is that the once dominant idea of a constant dark energy is now being questioned. Another central mystery is dark matter. Invisible yet gravitationally dominant, dark matter is believed to act as the scaffolding for galaxies and galaxy clusters. Without it, it would be difficult to explain how galaxies formed so quickly in the early universe. Yet despite decades of searching, dark matter particles have never been directly detected. This has led some scientists to explore bold alternatives that might eliminate the need for both dark matter and dark energy. One such proposal was introduced in 2012 by physicist Dr. Richard Liu, who questioned the idea of a single Big Bang. In his model, cosmic expansion and structure formation result not from one event, but from a series of intermittent mini-bangs or transient singularities occurring over time. According to Liu, matter entering the universe at different epochs could explain observed phenomena without invoking dark components. These events would be extremely rare and brief, making them impossible to observe directly. Yet they could leave subtle imprints in cosmic expansion and structure. Each event would temporarily add mass energy to the universe without violating conservation laws, creating effects similar to dark energy. In this model, the Big Bang represents only the first of many creation events, rather than a unique origin. Although highly speculative, this idea highlights an important point. Despite its success, the Big Bang model still leaves unanswered questions, and resolving them may require thinking beyond a single beginning. Which brings us back to the central question: what if the Big Bang was not the ultimate beginning? Modern cosmology increasingly entertains this possibility. In Penrose's cyclic universe, our cosmos is merely the latest in an infinite sequence of universes, each giving rise to the next. Other theories propose a big bounce, where a previous universe collapsed and rebounded into our own. In such models, time does not begin at the Big Bang. It continues through the bounce. Alternatively, time itself may have begun with the Big Bang, rendering the question of before meaningless, much like asking what lies north of the North Pole. This interpretation aligns with classical general relativity, where equations break down at t = 0. Quantum physics, however, challenges this boundary. Models of quantum gravity suggest that the Big Bang could be a transition rather than a creation from nothing. If dark energy evolves and eventually reverses, the universe might one day contract, triggering another bounce and a new cosmic era. For now, the question of what existed before the Big Bang remains unanswered. It lies at the frontier, where observation ends and theory begins, where imagination must be guided by mathematics but constrained by evidence. Still, science continues to make remarkable progress in uncovering the universe's earliest history. Will we ever find concrete evidence of a reality before the Big Bang? Perhaps not directly, but indirect clues may emerge. If our universe is one of many cycles, traces of earlier epochs may be encoded in the CMB, or the large-scale distribution of galaxies. If multiple expansion events occurred, subtle anomalies may appear in cosmic data. Or perhaps a future theory of quantum gravity will finally illuminate the true origin of everything. So, which explanation do you find most convincing?